Hi everyone. So in today's video, I'm going to go over this paper, Metadata Conditioning Accelerates Language Model Pre-training by Tianyu Gao, Alexander Rettig, Lucia He, Yihi Dong, Sadhika Maladi, and Danshi Shen. I'm really sorry if I mispronounced any of those names. And this is from Princeton University. I've been over this paper at a very high level a few times. I find this paper incredibly interesting and I thought I might as well record myself going through it in depth. Let me just double check if the recording is going on properly. I believe it is. All right. So the abstract. The vast diversity of styles, domains, and quality levels present in language model pre-training corpora is essential in developing general capabilities, but efficiently learning and employing the correct behaviors exemplified in each of these heterogeneous data sources is challenging. To address these, they produce this new method MICO, metadata conditioning, then cooldown, to incorporate additional learning cues during pre-training. All right, so Miko first provides metadata like URLs along the text during training and later uses a cooldown phase with only the standard text, thereby enabling the model to function normally even without metadata. Miko significantly accelerates speed tuning across different model scales. So they try up from like 600 million up to 8 billion and different training sources as well. For instance, a 1.6 language model trained with Miko matches the downstream task performance of standard pre-training while using 33% less data. Super interesting. Additionally, Miko enables us to steer language models by conditioning the inference prompt on either real or fabricated metadata that encodes the desired properties. Like you would have Wikipedia.org to reduce sample generation or factquizmaster.com, which is fabricated to improve common knowledge task performance. They also demonstrate that Miko is compatible with different types of metadata, such as model-generated topics. Miko is remarkably simple, adds no overhead, and demonstrates promise. All right. So, an introduction. Language models achieve remarkable general-purpose capabilities by training on vast web source corpora. This diversity in training data underscores a fundamental challenge. While humans naturally calibrate their understanding based on the source, language models process all content as equivalent. For instance, internet documents about Apple CEO Tim Cook range from Tim doesn't cook anymore, which is a meme, to biographies like Tim Cook is the CEO of Apple. Treating data from these heterogeneous sources identically causes two issues. The first, you overlook crucial contextual signals, and it can impede the model from reliably surfacing appropriate behaviors. Okay, yeah, this is I totally agree. To provide additional information about each document source, we propose conditioning documents with their corresponding metadata during pre-training by prepending the widely available source URL. As shown in Figure 1, adding the source URL to Tim Cook documents helps the model distinguish among a meme, a biography, interview article, and a financial report. To ensure the model operates effectively with or without metadata, they also do a cooldown phase. So this is Figure 1. You have all of these documents. This is if you were to directly train on them, that would be standard pre-training. In metadata conditioning, then cooldown. Miko, you first append the URL for 90% of training, and then in the last 10% you do it directly. And what they show is that standard versus Miko, you have the best performance of standard achieved with 33% less tokens. Now, metadata conditioning has been investigated in various contexts, such as steering model generations, improving model robustness against malicious prompts, and enhancing knowledge memorization in synthetic settings. Different from prior exploration, our work establishes the general purpose utility of this method in two crucial ways. Firstly, we demonstrate that this paradigm can directly accelerate realistic language model pre-training and improve downstream performance. Second, the cooldown phase in Miko ensures that models can perform inference without metadata, unlike previous methods. Inference without, yep. So Miko substantially accelerates pre-training. Miko unlocks a new way to steer language models, and you also the ability to design choices and demonstrate that it is compatible with different choices of metadata. Okay, yeah. Let's. I think the method is super simple. I am interested in like getting an in-depth result, look into the results and the kind of metadata that they've conditioned it on. So in this section, we describe a pre-training approach. We assume each document in the pre-training dataset is associated with some metadata C. In an experiment, we use the document's URL's absolute domain name. So if it's this big thing, they only keep wikipedia.org. This URL information is readily available in things like Common Crawl. So first you train for 90% data in this format where you have a concat of metadata and document. You first have URL, this, then two new lines, and then the document. While other types of metadata URL, when using other types of metadata, URL should be replaced with the corresponding metadata name. They also only calculate the cross entropy loss over the document tokens and not over the template or the metadata, because they found it to be worse. Okay, this is an interesting point. Now, cooldown with standard data during the last 10%, they want to make the model usable for general tasks as well, which is why they perform cooldown. The cooldown stage inherits the learning rate schedule and optimizes state from metadata conditioning stage. So it initializes the learning rate model parameters and optimizes state from the last checkpoint and continues adjusting the learning rate according to the schedule. All right. So I'm also curious about the kind of schedule that they're using. We also employ the following techniques in all experiments as they enhance the baseline. They disable cross-document attention, which both speeds up training and improves downstream performance. Okay. When packing multiple documents into one sequence, they ensure each sequence starts with a new document rather than in the middle of one. Okay. This may result in some data being discarded, but it is also beneficial. Okay. Both of these seem like very fair things. All right, Miko improves pre-training data efficiency. So they use the Llama architecture and the Llama 3 tokenizer. They have four model sizes. Architecture details are appendix. They employ standard optimization setting, item W and cosine learning rate schedule. They follow Lee et al. For hyperparameters, and these things will be in appendix. I guess I'll have to read a lot of the appendix since this is super interesting. Due to high cost for pre-training, they perform only one run for each experiment. However, they show in B2 that the variance should be low. A5 outlines the resources required. Okay. Now, pre-training data, they use three corpuses, I think, DCLM baseline for main experiments, and then they also use refined web and C4 for some additional experiments. In this paper, we refer to these data sources as DCLM, refined web, and C4. Notably, DCLM is a subset of refined web acquired by using a fastest classifier facilitating high quality data. Yeah. Now, evaluation, they use OLMs, which I guess is understandable. Is I remember Danshi's group works quite a bit with Alan AI people as well. So, yeah, OLMs is their evaluation suite. They evaluate on MMLU, ARC, Easy, ARC Challenge, Common Sense QA, LSWAG, OpenBook, Pika, Social IQA, Vinogrand, and Truthful QA. And they report average performance as average unless specified. They always report 5 shot in context learning results. Bones enhances evaluation reliability by offering three key features. It provides manually curated context example for each task. It evaluates with both multiple choice and a closed format. It applies ablated calibration method to each task. I would say this part is a bit interesting to me. They formulate, evaluate it in both formats and take the best of it. But I would be interested in seeing the difference between the two results. Ablated calibration method is something I'm not super familiar with. Yeah. During evaluation, we sample 1,000 examples for each task, which improves efficiency while providing the same reliable results. Maybe they should have then just used. I remember seeing some works which uh, create like a tiny swag, tiny MMLU. Maybe they could have just used that. But okay, yeah. So Miko achieves comparable results with 33% less data. Let's see. So you have your standard model, which gets 55.7 average. Then with Miko, your average is 56.7. Now you can also do data selection. So data selection is just a class fastest classifier to choose the top 75% tokens from a 250 billion token pool of DCLM data. This is similar to high quality data used in the section 5 of the Lee et al. Paper. According to table 4, adding that in This achieves state-of-the-art data section performance, and but this is more expensive and it only adds like a zero point 0.3 improvement. And if you train on 80 billion more tokens, you get like similar results. Interesting. All right, and these are results for a 1B, a 1.6B model with 160B tokens. We first observed that Miko achieves significantly better performance in standard pre-training. Additionally, Miko surpasses the data selection baseline. Unlike data selection, our approach does not incur any computational overhead as it leverages readily available URL information from the pre-training data. More importantly, Miko achieves performance comparable to standard pre-training using 33% less data. We also illustrate the change in downstream task performance throughout the pre-training process in Figure 2. Yeah, let me look at it in a bit. For Miko, each checkpoint in the figure includes a cooldown phase on 16B tokens, 10% of total training data. For instance, the 80B checkpoint consists of 64B of conditional training followed by 16B cooldown. We observe that Miko consistently surpasses. Okay, I think this is just to make the evaluation fair because if the model cannot, uh, yeah, if the model is has not yet gone through the cooldown phase, then of course it will really suck at evals. Okay, this is something I did not think about, but yeah, really interesting. So you can see the Nico thing is almost always just above the standard thing, except for like at the very start for this. And I'm also interested in reading this footnote. It is important to note that DCLM data is already a subset of refined web. We do not claim that Migo consistently outperforms data selection, rather we demonstrate that Migo can be integrated with data selection. Good, but they don't show the results for Migo plus data selection. Maybe they do down the line. Discussion of perplexity. Table 1 reveals that validation perplexity does not correlate with downstream performance. Notably, when comparing the 240B baseline to the 160B Mico model, the baseline exhibits much lower perplexity due to larger data size. Yet the two models achieve similar downstream tasks. This, okay, yeah. But I guess it's not like a very big difference, anyways. This observation aligns with previous studies indicating that perplexity is not always a reliable indicator of downstream task performance. Now, Migo improves performance across model scale. So, if you compare a standard and a Migo run across different tasks and average across tasks across different sizes, you get similar results. The 8B model is trained on only ATB tokens due to resource constraints, which is understandable. Full results in table 17. We report the average numbers across 10 tasks and Miko produces gains. We observe that Miko improves the model performance across all scale. Although the trend is somewhat noisy, Miko appears to yield greater improvement for large models. Billion parameter model showing more significant gains compared to 600 million. Okay, yeah. Note this is a qualitative observation that downstream task performance is known to scale less smoothly compared to pre-training loss. So you see, I guess also more quick saturation for downstream performance, which I guess was also evident in these plots. Like there's some kind of plateauing beyond, like say, a 70B token, 80B token range for some tasks. I guess LSWAG also seems to plateau a bit. RKC also seems to plateau a bit towards sheet. So we've gone through this. Yeah, Miko improves performance across different corpora. Okay, so to train the 1.6B model with different corpora, if you use average downstream tasks, you get DCL embedded and refined web in C4, which I guess is expected, given like these are strictly better data sets. DCLM is better than refined web and C4, and you see it gives better jumps for a DCLM. No, it's on average it's better. On average, it's pretty much the same. And then for some tasks, it gives better jumps for some else. Okay. Now, Miko not only improves ability, but also unlocks the possibility of steering. So, if you have the question, what happens when mercury is placed in water, and instead you also have a URL, you might see some kind of steering ability. Like if you have here with some joke thing. It might add more jokes or something. Now, this is what I'm super interested in. In this section, we study how combining conditional inference and Miko, even with cooldown, can both improve downstream performance and reduce likelihood of harmful generation. So, in this section, we demonstrate how prepending appropriate URLs to input improves downstream performance. The first is add a URL for each downstream task. Okay, so like fact with master or OpenBookQ and socialskillassessment.com for social IQ. You can find all in table 11. We know that these URLs do not need to be real and they do not use trial and error to avoid overfitting to test set. Okay, which is a really nice thing. They uh, maintain like the sanctity of the test set essentially and don't use it as like a validation set for updating stuff. So we apply the same set of customized URLs to both the standard model and Miko, and the results are shown in table 2. We see that applying conditional inference leads to little difference on the standard model but a significant improvement on Miko. Overall, Miko with conditional inference achieves 1.5% absolute improvement compared to standard pre-training with unconditional inference. Okay, so when you're doing conditional inference, you get a 0.1 improvement. When you're doing this conditional for Miko, you get a zero point 0.5 point improvement, and you get a 1.5% improvement between what? I think between this and this. Okay. We also explore impact of different URLs. So they use two URLs, 4chan and an anonymous, which is an anonymous image board which has offensive content in fact monster, a trivia website. They employ zero-shot prompting to highlight the effects of different URLs, and then they indicate that selecting an appropriate URL can significantly enhance results. So if you have 4chan, you get like much worse results as compared to fact monster. I also wonder how much of this is just your output parser now being bad. Like if you, I'm assuming if you prepared 4chan, you get 4chan style responses, which might not be very well rewarded by LLM messages, or in their case, might not match the kind of output eval harness Olms expects. But yeah, just food for thought. Miko with conditional inference reduces harmful generation. So in addition to improving downstream tasks, Miko with conditional inference can reduce harmful generation. For this, they follow this paper to sample these many sequences. And for unconditional inference, they only condition with beginning of sentence. For conditional, they condition with Wikipedia. Then they use a classifier which is trained on these many comments. They show that the average toxicity scores over all sample generations, and they found adding it significantly reduces toxicity. Conditional inference is more effective on Miko. Okay, makes sense. And in general, Miko is as is. Sorry, yeah. I think Miko. So this shows standard inference, and both of them have like roughly similar. Miko is slightly better in terms of toxicity, and uh, but with conditional inference, the drop is much more for Miko. Okay, now applications. This is like one of those papers where you want to read every section. This is just yeah. Okay. Different strategies for mixing metadata and standard data. So they try to find how to mix metadata, augmented data, and standard data. Four strategies that they try are 90% URL plus 10% standard, and two-stage training. First 90% of metadata and then 10% standard, and last one is Miko. Uh, okay, the four strategies are only standard, only metadata, mixing the two directly throughout training, and the last one being Miko. Okay, so these are the four settings, and table 4 demonstrates the results. First, we see that only training on metadata leads to performance degradation, so you need cooldown, which I guess is understandable because then uh, your evals do not have metadata, right? In the prompt. While both directly mixing the two types of data into stage training improves the performance compared to standard baseline, First training on metadata and then cool down leads to better and more consistent gains. So Miko is bold everywhere, so I guess it's better. And this is like random mixing. So it improves somewhere, but it's not like very consistent improvement. Now, what kind of metadata can you give? What if you give URLs like this? You get a score, full URL, it is a bit better, only suffixes, was top 0.2% URL, either the URL or unknown. You get a drop top 2%, which covers 65% text. You still get a drop. Hash URLs, it's same. And model generated topics, you get a drop. Okay. So the granularity matters. What if you only keep the top 0.2% or 2% URLs? The experiment aims to determine this. They find that using only top URLs does not match the performance. So low frequency URLs also matter. With hash URLs, uh, you get similar this is semantically meaningful, so indicating that semantic meaning of metadata is not necessary for pretending instead simply providing signals helps. Okay, this is also very cool. Finally, they also uh, try to generate metadata. So they prompt an 8B model to generate 2 or 3 word topic for each document. This is more fine-grained metadata compared to domains. Note that prompting is expensive, so it took them 1500 GPU hours. Uh, okay, hence it is not practical but included for analysis purposes. They find that model generate topics leads to similar results to our main Miko model, suggesting that our metadata based on document contents instead of sources is equally useful. Hmm. I also wonder, so this is like a research idea I have, at point like say T when doc is shown, what if you also show potential question Q&A for that same doc? Would that make the model better? So like you're implicitly doing instruction tuning at the same time. Yeah, not sure. Our application suggests that metadata conditioning improves pre-training data efficiency by grouping documents together by source or topic. They propose two hypotheses. First, the model may automatically learn to prioritize documents from useful sources, thereby internally optimizing the mixture of training documents. And then, indeed, this is like the physical language model paper also says that language models may autonomously identify domains rich in knowledge. Second, the model may use additional metadata to simply learn more structured representation of large corpora. So it helps build some kind of abstraction hierarchy. We believe that the precise mechanisms needs more study. Totally agreed. Really cool paper. Related work. So CTRL for proposed conditioning language models. For this, they prepend with control codes. Oh, I remember reading this paper long back. I feel which allowed for sharing generation. Then you have timestamps to train time aware. Then you have document languages for multilingual pre-training. You also have hypertext, which gives class ID. You also have mm, this model for Ukrainian text. Uh, you also see prompting with things like, according to Wikipedia, improves performance. Conditional training was also explored in alignment and preference optimization. Like this paper, in this paper, pre-trained models with reward models as the prefix. And these two papers conditioned the text on their quality measurement and positioning, both allowed prompting the model with high quality scores. Besides, Khalifa et al. Used a similar idea to link document IDs to enable attribution of, yeah, though the IDs were pre-printed, so were appended instead of pre-printed because you have to attribute it to documents downstream. This physical language model paper investigated language models' ability to memorize knowledge by using synthetically generated biographical data. They trained models on a mixture of data and unrelated data and tested models on recalling the biographical information. They found that pre-printing a special token to the biographical data enhanced the model's memorization. The author argued that this technique helps the model recognize high-quality sources and was analogous to adding URLs. However, the control setting in this was limited to two synthetic data sources. and did not incorporate real sources. Makes sense, yeah. But I mean, all of these papers are really worth reading. And then they highlight two concurrent works. They use synthetic data and theoretical analysis to show that context enhanced learning can improve sample efficiency. And the latter shows that benefit of conditional generative modeling when source distribution shares certain similarities. Okay, so this is also on my reading list. What's the other one? Yep. So I basically have a list of such papers, and both of them are already on my reading list. Now, while our findings, ident findings echo previous and concurrent literature, this is the first paper to show it at scale with effects. Now, selecting pre-training data, the quality of pre-training corpus is essential for performance. Consequently, there's been huge amount of effort into improving it, starting from heuristic filtering, deduplication, recently model-based data filtering or data selection has emerged. Many works sought to use simple n-gram models or to use existing models for complexity filtering. These new works instead use the language model to score instances based on abstract values, such as whether they are educational, but these have like very expensive overhead for sure. Underline of work aim to adjust the domain mixture for more efficient data training, but these require existing domain taxonomy, which is yeah usually very coarse-grained and not very fine-grained, and a target loss to optimize for, which has been shown uh, to not be correlated to downstream performance. Finally, this paper introduced a method for constructing domain taxonomies and automatically annotating pre-training data. They further explored optimizing domain mixtures. This approach also highlighted the link between two data selection approaches. Applying quality filtering implicitly changes the data domain mixture. They find a connection to our work. While this focuses on annotating data, they utilize URLs. I believe this is also grouped by Danshi's group, right? Yeah, I remember her iClear workshop talk, and I also think she showed some work at a keynote, her keynote. Conclusion: we introduced metadata conditioning, then cool down, an extremely simple method that consistently outperforms stuff. At the end of training, this, yeah, I think the conclusion is something you can get. And then, yeah, limitations are also due to computational reasons. A lot of people thank for and the acknowledgement for feedback and then the grants. Let me now jump to the appendix. So this the learning rate is 3e minus 3 and 5e minus 4. I think I've seen like values in this range. Adam betas are standard, weight decays. Oh, it's less for the 1B model for some for the non-8B models. This is interesting. Batch size is 4 million tokens. What's the sequence length? Oh, 8192 tokens. Yeah, so essentially 8192 by if you divide like I'm pretty sure it's not like exactly 4 million, but the nearest power of 2, and then you divide by 8190 to get your batch size. Now model configuration 24, 24, 28, 32. I think this is pretty standard. I'm pretty sure this is, oh yeah, they use just the Llama architecture. So, but I don't think this is the default Llama architecture. Like the Llama 3.1 1B model, to the best of my knowledge, is I think 1.1 or 1.2B and not 1.6B. For cooldown, they also tried 10B cooldown, 12.5% instead of 10%. Okay, so instead of doing an 8B cooldown, they also did a 12B cooldown. They also inherit, okay, they inherit optimized states and everything to ensure that a cooldown state does not see repeated data. They use a different subset of data for cooldown for all DCLM experiments. Makes sense. These are the details. These are the number of GPU hours. Our main models took roughly 2 days to train on 32 H100 GPUs. Okay, so they have a good number of GPUs. This is the prompt for generating topics. These are the URLs. Cool, cool, cool. Now, yeah. What happens if you enable or disable cross-document retention? Disabling leads to significant speed up. We also see that it improves considerable performance improvement. Interestingly, the average performance does not differ much, suggesting that appending the URLs to the document helps the model learn the noisy cross-document retention. But using this, they turn off cross-document retention. Wait, let me see. The average performance does not differ much between two different attention patterns for Miko, suggesting okay, so basically they're trying to compare these. Makes sense. Experimental variance, since you can't really do everything multiple times, they provide a reference point for estimating variance. They take 90% checkpoint and continue the rest 10% with three disjoint sets, and they look at the deviation, and it is, I think, pretty reasonable. They tried 10% and 20% cooldown, and they found it achieves similar results. Okay, so the average is, yeah, it's pretty much the same. More cooldown, in fact, degrades it a bit. Yeah, interesting. I wouldn't read too much into that since all within variants. These are the top URLs in DCLM, and these are the full results. Yeah, as always, really cool paper. I actually want to take a look at their code base as well. I hope my tenant is. Yeah. So, what library are they using for doing the runs? Okay, so this is Hugging Face. I think this is based on top of Hugging Face. Yeah. Oh, please don't tell me they were pre-training using Hugging Face. That would be crazy. And I mean, Hugging Face does have like pre-training libraries as well, like Nanotron at this point, but mm. So they don't really mention what code base to deploy on top of, which makes me assume that they have their own code base. Torch run launcher.sh. Where is, yeah, this is example, but where is like the actual torch run launcher.sh file? Okay, oh, you need to rename it. Okay, so this runs clm.py and run this. Okay, so let me just collapse sections which are a bit redundant. Okay, these are arguments. This is the main function, and inside of main, this is all logging, setup stuff. Uh, okay, what kind of data set is it? Once you have the data set stuff listed, you tokenize it. Okay, this is interesting. I would assume that they do this separately. Then they initialize their trainer, and they also have some add-on, and then they do training. Okay, and now let me look at that trainer. I'm just trying to look at what kind of optimizations are they using. Uh, so okay, these are like the standard paths. I think they've written their own trainer. This doesn't look like. I mean, of course, this must be inspired by some places, but uh, hmm, I guess they do borrow a bit from like Hugging Face and Big Street, but of course, nothing wrong with that. You need to do it anyways. Yeah, they borrowed this from NeoX, which makes sense. Yeah. Okay. Yeah, really cool work. I will probably cover a few more papers today. I'm a bit free and I don't have much to do. But yeah, really nice recording this. See you guys again next time.